All right, next up we have Seth Wiedman presenting on increasing the impact of AI through better software. Seth is a data scientist at Facebook who works on the PyTorch team to improve tutorials, documentation, and overall developer experience, as well as writing new tutorials when new features are launched. He most recently built solutions to machine learning problems at Facebook. And prior to that, he taught data science as a founding member of the corporate training team at Metis. And prior to that, he worked at Trunk Club, using machine learning to help them sell clothes. He is passionate about trying to explain complex concepts simply, and recently published an introductory book on deep learning with O'Reilly called Deep Learning from Scratch. He has mathematics and economics degrees from the University of Chicago. Please welcome Seth.
Thanks, Peter. Hey, everybody. So I'm kind of curious on this audience. How many of you feel like you're familiar with deep learning? Okay, about almost everybody, or 2/3 or so. And if you're not, that's totally fine. And how many of you would you say are familiar with PyTorch? Okay, about half. Cool. So this talk, I'm going to give an intro to PyTorch and talk about what it is and how we use it at Facebook. But I'll also try towards the end to share some new stuff that even those of you that are familiar with PyTorch might not know about that, so hopefully you can learn something as well. All right, so we'll talk about what is PyTorch, then a little bit on how we use it at Facebook, and talk about some things that are new, and then briefly share how you can get involved at the end. So what is PyTorch? So PyTorch is a deep learning framework that lets you create deep learning models. So it supports both eager and graph-based execution. So that means you can just define your models step by step and say, like, it first does this, then does this. Or you can, once you've defined your entire model, you can run data through it and export that as a graph that can be run in some sort of production environment. We support dynamic neural networks. You can have branching within your models. You could say, if this happens, then this, else this. We support distributed training, so you can train your model on one machine across multiple GPUs or even across multiple machines, and we'll touch a little bit on that towards the end. We support all the hardware accelerated inference you might expect, so GPUs, support for NVIDIA, as well as different ASICs. And a big thing with PyTorch that those of you who have used it hopefully appreciate and we strive for in every new feature that we build is simplicity over complexity. So trying to keep the user experience extremely simple and clear, so it's extremely clear how to use all the functionality. So what are the different building blocks of PyTorch? There's, here are some of them. So torch.nn is sort of the core of it. Torch.nn contains all the building blocks that you use to create deep neural networks. So all of your convolutional layers, different variants of recurrent neural networks, and so on. Once you've built a neural network, one thing that we use a lot at Facebook and people are starting to use more and more is torch.jit. So once you've defined a model, you can just either trace input going through your model or script your model so that you have a graph that you can then use in some sort of production environment. When training these models, we used optimizers from torch.optim as well as the autograd features from torch.autograd. And one of the main use cases for PyTorch is training computer vision models and deploying computer vision models. So vision has sort of been a first-class citizen of PyTorch from the beginning. So we have torch.vision to support that and torch.data to support data loading, primarily for vision models, but you can also write your own custom data loaders, and we have tutorials on how to do that for NLP use cases as well. So for those of you that haven't seen sort of how simple it is to define a neural network and run it in PyTorch, this will be an introduction for you. So defining a neural network in PyTorch is as simple as defining a class in Python that inherits from nn.module, which is sort of the base class for all neural networks. Within that class, in the init function, you can define some operations that are class variables that your class can use. And then you just define a forward function that says how data is supposed to be fed forward through those different operations. And we support all the standard operations that you can use, that you might want to use in a neural network. And so here you can see that we're using like self.fullyConnected1 and fullyConnected2, the things that we saved as class variables in the module. So you just define a simple Python function. Once you've defined your model, you can instantiate it using that first line and net equals net. And then we make it easy to sort of, the standard flow with neural networks is you define a model, then you want to sequentially feed data through it, or sequentially load data into memory and feed data through it. Why do you want to do that? Your data might be too big to load the entire data set into memory. You just want to sort of sequentially load batches of data and feed it through your network. So the data loader class provides that. And SGD is just one of many optimizers supported by PyTorch. And you can see that the optimizer is sort of tied to the network itself that we defined above. And once you do that, this is sort of the standard training loop in PyTorch. So again, just pretty readable, straightforward code. We load in from the data loader our sort of features, whatever our features are and whatever our target is. We make sure that our gradients are zeroed out. We feed our features forward through the network, and we then compare the result of the predictions our network made to whatever the target is, and get some loss value, and then we call loss.backward. And loss.backward is sort of this magic thing that remembers all the computations that were performed to compute that loss, and therefore is able to figure out for every parameter in the network how much will increasing or decreasing this parameter affect that loss. And then the optimizer then knows how to increase or decrease the parameters so that the network learns on this iteration. And then, we can save our model every few epochs or whatever, just using torch.save. So pretty straightforward. If you want to learn more, there's a 60-minute blitz we have that's been pretty popular since we launched PyTorch. Definitely go check that out. Okay, cool. So how do we use PyTorch at Facebook? So what is the problem we're trying to solve at Facebook? At Facebook AI Research at FAIR, there are lots of research projects going on that are constantly trying to build better models to, say, classify hate speech or prevent certain images from being seen on the platform. So the research process is, you might try different approaches, you might prepare these huge data sets, do a lot of work to clean them, train lots of different models, and so on and so forth. But then you get to the point where you actually want to transfer this model over to production. And not only do you want to transfer it to production, you actually want to scale out this model so it can be hit, hundreds of millions of times in a day. So how do we do that? So fundamentally, the problem we're trying to solve is to make that last step as easy as possible. So researchers, and maybe many of you have probably trained deep neural networks either on your own laptops or on various cloud platforms. And it's not too hard these days to train a deep neural network and get a model that solves some problem that just years ago would have been unsolvable just by cloning some GitHub repo, maybe changing the code, or maybe doing something original yourself. But then the question is, how do you deploy that model out so that it can be hit by some massive production service? So that's sort of one big problem we try to solve at Facebook. And this was sort of the big thing that PyTorch tried to solve leading up to the big 1.0 release, which happened almost exactly a year ago. And so we'll talk more about what does working in production actually mean? Well, there's a few constraints of what you have to solve if you're going to run a model in production. First, you have to actually use all of the hardware that you're given. So if you're not using all the hardware you're given, if you're not using some CPU cores, if you're not using the GPU when you should be, then you're going to see a big performance hit and a big cost increase. So at Facebook, we definitely care a lot about that, and other companies who want to use PyTorch in production will care a lot about that. Scalability, of course. So you have to have something that runs extremely quickly, that can not, of course, train on huge data sets. You need distributed training and things like that. But you also need to do lots of inferences per second, potentially billions. And so in order to do that, as you know, Python isn't the fastest language in the world, even though it's great for prototyping, and it's probably the first language that many of us really fell in love with. But to be able to do these billions of inferences per second, you really have to be able to interop with languages like C++ that are extremely high performance. Or things like Java, if you want to run a model on an Android app, for example. And this sort of hits on that point. So whatever you deploy has to be cross-platform. So you can't have a model that only works on this, if it's running on this computer with this Intel chip and this NVIDIA GPU. You need something that's some intermediate representation that's cross-platform that can run on many different kinds of devices. And of course, you need something that's reliable. Training jobs might run for weeks. You know, some of you may have trained models for a long time, either on your own laptops or on cloud instances. You might have used many, many different GPUs, so you need to be reliable in that sense. And the way we tried to solve a lot of this was using torch.jit. So I'll show some code snippets a little bit later on what this actually is, but essentially this is, we think, a really fast way to go from a model that you've experimented with and you're ready to sort of ship to production or go live with. It's a really fast way to get that to production. And the way you do that is you essentially take the model that you've built, you extract an intermediate TorchScript representation of that model, and then you can further optimize that intermediate representation on different pieces of hardware and deploy that across multiple platforms. And again, the key here is this really allows researchers and probably most of the people in this room to write models in eager mode. So just prototyping different models and not worrying about what the ultimate representation of the model that's going to be used in production is going to be. But then quickly, once you're done with your prototyping mode and you want to ship something to production, quickly get something scripted so that you can actually deploy it to production. And one other thing I'll say is that this is actually, this model has allowed teams at Facebook that are collaborating, but it has allowed actually teams like at FAIR that are researching and constantly building new models to collaborate very closely with product teams and actually in many cases use the same code base. Because the only difference between what the two teams are using is that the product team is using a scripted version of the model that, as you'll see, is pretty easy to produce. And the research team is producing a not yet scripted version of the model. So for example, if you're trying to use if you're trying to predict what the correct, in Facebook Messenger, we have suggestions on how you might like to respond to whatever somebody said. And if you want to, if you want to prototype different models that could be used there, you need something that can do billions of predictions a second, and so on and so forth. And you need the product team to be deeply integrated with whatever the research team is that is going to produce that model. And so this JIT, which has allowed us to quickly move from a model that's built by a research team to one that can be used by a production team, has enabled this to go much faster. So here's sort of like the way this actually works with Messenger next sort of response prediction. So the research team works in PyText. So PyText is sort of a series of building blocks built on top of PyTorch that allows them to prototype different models. And when they have a model that they're ready to at least try out, they can actually ship it to a Python service that just takes a small amount of production traffic and sees whether that model has a significant increase, positive or negative, on whatever metric they're trying to drive. Once they're ready to actually go live with that model and deploy it more broadly, they can quickly export it to TorchScript, maybe tune the performance of that exported model on different platforms, and then deploy that into whatever really high performance runtime is needed. So that can be C++ if you're just dealing with web traffic, or if you're trying to deploy that model locally on a device, it can be whatever you need for iOS or Android. Cool, so that's sort of high level how we use PyTorch at Facebook, and I'd say the general flow for how different companies are starting to use PyTorch in production. All right, I want to talk about some new stuff. So for many of you, a lot of that will be review, and you've sort of played around with PyTorch a lot, and you know sort of the basics. So I just want to highlight some new stuff that hopefully you'll find interesting. So we have these two new domain libraries that we made a lot of improvements to in PyTorch 1.2, which came out in August. And I'll just run through a couple of highlights of these. So Torch text, we have data sets for translation, for sentiment analysis, for lots of different popular NLP models that you might like to train. And we do a lot of the really annoying pre-processing that you have to do whenever you want to train NLP models on some advanced task. We have functions that handle a lot of that for you. I'm not advancing. There we go. Torch Audio. So Torch Audio, similarly, we have a labeled speech data set, this VCTK data set, which is well known in the audio community. So just audio files along with the actual words that those files represent. And I think this is really cool. A lot of common audio transformations, like transforming these raw files into spectrograms, are actually implemented as nn.modules, meaning you can include them in your neural networks and backpropagate through them. So you could imagine taking a raw audio file, doing a spectrogram, and then maybe putting a convolutional neural network on top of that, and you can backpropagate through that whole thing, which is cool. I'm not advancing. That's weird. So yeah, learning more on this, there are like 3 torch text tutorials on pytorch.org/tutorials and 1 audio tutorial. So definitely encourage you to check that out. Okay, let's just talk about TorchScript really quickly. So just want to make it clear, it's very easy to use TorchScript. We sometimes get questions that like a lot of people that are even power PyTorch users haven't heard of TorchScript or aren't so familiar with it. So let's just say we've defined some simple module in PyTorch, some toy module that just does some simple operations on the forward pass. Sort of translating this into TorchScript is really this easy. We just call torch.jit.trace on an instance of that module and some data that we want to pass through it. So that's how easy tracing is. And then once we've traced, so you can actually see the intermediate representation of it using .graph on the trace cell, or you can just see a more human readable version of it using .code. And you can try this out and print these and see that the traced version and the original version produce the same output. And that'd be a lot faster if you shipped that to production and ran data through it. Another thing is, for modules that have branching, you can use you can use script instead of trace. That's a key thing. And we have a couple good tutorials on this. The Introduction to TorchScript tutorial was written by 2 of the engineers that worked most deeply on this feature. So definitely check that one out. And then we have a follow-on tutorial that shows you how to load your traced module into a C++ app, for those of you that are interested in the performance stuff here. All right, distributed training. This is another thing that I think is underappreciated, the PyTorch functionality here. So there's 3 different levels of distributed training that we support. There's data parallel, which I think people are most familiar with, which is just if your data is coming in large batches, you can, on each time you call the data loader, you can split the data across multiple GPUs. So you can have one GPU, processing half the data, another GPU processing the other half. ModelParallel requires a little more work to configure. You actually, when you define the model, send certain parts of the model to one GPU and other parts to another GPU. So you're actually splitting the model across multiple GPUs. So why would you do that? You might have some huge model that's too big to fit on one GPU. So you can use that with PyTorch. And then distributed data parallel essentially does data parallel, but in multiple processes. So data parallel is just single process, but multi-threaded. And distributed data parallel also works with model parallel. So if you have a model that's too big to fit on one GPU, you can do data parallel on that model that's too big to fit in one GPU. And this is all pretty straightforward. So data parallel, it's as simple as, you write your code to get the device, which is code probably many of you are familiar with if you've used PyTorch with a GPU. And then if you have more than one GPU, you can just call model equals nn.dataParallel model. And again, anytime you feed data through that model, if you have more than one GPU, for example, it'll automatically split your batches into, say, 2 or 3 and feed them through the GPUs in parallel. So that can speed up your training quite a bit. Model parallel, the way you'd use model parallel is, again, if your model was too big to fit on one GPU, you might have to take some components of your model and put them on one GPU, and then take another components of your model and put them on another GPU. So if your data was small enough to just fit on one GPU, you probably wouldn't want to use this, but you might if your model was too big to fit on one GPU. But you can get around some of this with distributed data parallel. And this requires more setup. You actually have to initiate process groups and stuff because you're doing multiple processes here. But the way this works, and there's a more detailed tutorial on this, is essentially you define your model across these multiple device IDs, and then you just call DDP, which is distributed data parallel, on your model and the device IDs. And a key thing here is this also works with ModelParallel. So again, if you have a model that's too big to fit on just one GPU, you can still use this same code with that model that you had to split across multiple GPUs. So hopefully that's some good new stuff for those of you that are already familiar with PyTorch. And we have tutorials on this. So these are written by, again, like the engineers that build a lot of these features and that continually work on improving them. So we have 2 tutorials, ModelParallel best practices, and then getting started with distributed data parallel, and then 2 even more advanced tutorials that really show how to dig in and optimize this. So how you can get involved? I'd say for those of you that are more beginner or at an intermediate level, definitely check out our tutorials. We have good tutorials, a lot of beginner stuff, and then good tutorials on vision, good tutorials on text, and some of the ones I shared here, as well as other ones on like reinforcement learning that I didn't cover here. And for those of you that are intermediate advanced, we love contributors, so please submit an issue, submit a pull request if you want to contribute. And we also have examples that are less sort of commented and less like walkthroughs, but if you go to the examples repo, you can see lots of examples of, for example, training a GAN using PyTorch, and you can just clone that repo and be off and running.